to be here in TIFR. So today I will be telling you about universality in microcanonical entropy at large spin. This talk will be centered around conformal field theory, and we'll see that I'll define a class of CFTs for which this universality emerges in large spin, and in due course I will explain you what class of CFTs I am talking about in this case. So let us begin. So this talk will be based on these papers that we put out recently, a couple of weeks ago, with Jaishin Chao from EPFL and Bart van Ries from École Polytechnique in Paris. So I have given many talks here, basically centered around this theme of finding universality in density of states in conformal field theory. So, but still, I would like to warm you up with some basic gentle introduction. So let us start with some very basic question. So given a quantum system, what is the most basic yet powerful question that you can ask? And the answer is simple, that you want to know what is the spectra of the Hamiltonian. Of course, if you are given a strongly coupled quantum field theory, it's almost impossible to diagonalize the Hamiltonian or find its spectra. So this is a hard question. So what we want to do, instead of diagonalizing the Hamiltonian and finding the spectra explicitly, we want to impose some symmetry conditions on these quantum systems, and we want to find some universal features of this spectra of the Hamiltonian. So in particular, we would like to ask, given a quantum system, what do the asymptotic spectra of the Hamiltonian look like? And by asymptotic, I mean large energy or large spin, or any sort of quantum number which you can take to be very large. So for example, here you have three depictions of the energy spectra, for example. So all these horizontal lines are energy levels. So you can ask what is the average density of states as you go up in the upward direction, as you make the energy higher and higher. And you can ask also refined question like what is the label spacing, whether the gaps becomes larger or larger as you go up, whether the gaps are regular, so the energy levels are integer spaced, or whether this third option where the spacing actually goes to 0 as you go to the higher and higher quantum number. And you want to know whether there is some universality in all these features when you go to high energy or high speed. And of course, yeah.
The system is chaotic at high
temperature. Yeah.
Then is there anything known in general about the spectrum, just from the fact that, okay, if it's chaotic, let's say that means random matrix theory.
Yes, exactly. Yes. Yes. So in that sense, so that's what I was going to say in this slide. So the asymptotic spectra of a quantum Hamiltonian reveals deep insight about thermodynamic properties at high T. In particular, it also encodes the nature of dynamics, whether it's chaotic or integrable. So in particular, in a integrable system, you would imagine the spectrum is regularly spaced, or it has a Poissonian statistics. Whereas in a chaotic system, you would like to get go, you need to define a statistics. And to define a statistics, the spacing needs to go to 0. So you would imagine this third option is an indicator of a system being chaotic. And top of that, you will see finer features like level repulsion and random matrix like theory. So yeah.
Just asking the experts, there are these two criteria for chaos now. There's the Wigner criteria in terms of spectra, and then there's the criteria coming from Botox.
Yes.
I definitely know of examples where you have the Wigner distribution, but where you don't meet the criteria vis-a-vis Botox.
Yes.
But I don't know whether the other way around is possible. Namely, does the spectrum have to be a random matrix type as a necessary, if not sufficient, condition for all the various attributes of chaos? I find it an interesting.
Yeah, I think it's not. Yeah, it's not settled. I don't think so. And another example I can give you, which is aside from the talk, but so if you take hyperbolic manifolds, our whole beloved thing, because of the negative curvature, all the geodesics will diverge. So in that sense, it's a chaotic system. So it has a positive Lyapunov exponent. But then there are two classes of hyperbolic manifolds. In one class, the statistics of the eigenvalues are Poissonian, so it's integrable in that sense. And in other class, you have random matrix. So that's one example where so OTOC is a signature for Lyapunov exponent. So here the positive Lyapunov exponent doesn't guarantee you random matrix.
Well-known even 2-dimensional.
Yeah, even 2-dimension. Yeah. In fact, the RMT ones are the generic ones. In fact, the arithmetic ones where the spectrum is integrable is kind of spatial points. And mathematicians are mostly interested in the arithmetic ones because they have nice properties.
Classical.
Yeah, the Lyapunov exponent is the classical chaos. But in the quantum sense also, there is something called quantum unique ergodicity, which basically is, suppose you solve the Laplacian equation. So it's like you put a free particle on the hyperbolic manifold and consider the probability distribution associated with a wave function. As the energy goes to infinity, the probability distribution associated with the energy eigenfunction basically spreads out all over so it becomes a uniform distribution. So in some sense, it's also, you can see this is a feature of chaotic theory where it basically explores all the phase space. Sorry, what is the emissions? This bound? I don't think anyone has computed OTOC in this quantum setup in the hyperbolic manifold case, but
So nobody has taken one of your arithmetic manifolds and put a conformal field theory on it, say, and tried to ask about the OTOC, or something like that. Right?
yeah, or even like, yeah, just particles. Yeah.
So you can do OTOC.
Yeah, I think because you just, yeah, but I would imagine if classically there is a Lyapunov exponent, I would imagine quantum mechanically it will still be there. That would be first case, but
Thank you.
no, it's fine. So yeah, at the end of the day, the reason we are asking about the asymptotic spectra is basically we want to understand thermalization at the level of subsystem, and we basically want to answer all these questions that Sandip was asking, like how to characterize chaotic systems, whether there is a, like the ideal deal would be you would come up with a list of necessary and sufficient conditions, and someone hands you something, you just check the list, and you basically tell that this system is chaotic or not. Oh, the fast spacing is like you cannot even define statistics because in some sense the spacing becomes larger and larger. And in fact, as I will show later, the fast thing cannot happen in a conformal field theory. So it's ruled out by consistency conditions. So only the second and the third options will be viable option. And between the second and third options, the second one is feature of integrable CFTs. And the third one should be a feature of chaotic CFTs. And I will define a class of CFTs for which third one is a viable option. So we'll go there slowly. Okay. And of course, on top of this, basically ADS CFT gives you, before ADS CFT, I should, because we are applying this on conformal field theory. And the reason we want to focus on conformal field theory, because conformal field theory hands you some tools, non-perturbative tools. You have lots of consistency conditions like crossing, modular invariance. And the idea is that you can use these consistency conditions to say that the observables are highly constrained. So if you ask this question about asymptotic spectra of Hamiltonian in the context of conformal field theory, the idea is to use this conformal bootstrap analytically to say something universal. And we will see this explicitly in the talk. And then basically this is the refined question that given a conformal field theory, what do the asymptotic spectra of the Hamiltonian look like? And the ADS CFT gives you basically another layer of motivation to this question, because we know the asymptotic spectra of a CFT provides insight into quantum nature of the black holes. So if you can say something about the high energy states in CFT, you basically are probing the black hole physics. You can talk about entropy of black holes, you can talk about physics of near extremal black holes, how their quantum corrections are. And you can say like when does the black hole saddle dominate in a putative gravitation path integral and so on. And of course, in the context of 2D CFT, for example, if you want to probe this, you need to go to the holographic regime, which basically means you have to take central charge going to infinity limit. But the basic fundamental question that what are the universal feature of the asymptotic spectra remains useful or meaningful even in this context. So today's talk, I will not go into central charge going to infinity limit, But whatever I'm going to present, there should be analog of that story in this setup. Okay.
We impose that the low-lying spectrum is sparse.
Yeah.
And then ask about
Yeah. Yeah, so there we need to impose more conditions to probe the large central charge. So of course, the most celebrated result in this context, that what does the asymptotic spectra look like, is came from Cardy's formula, which is basically says that irrespective of what the underlying Hamiltonian is, like if you give me the central charge of a 1 plus 1D CFT, which is basically related to Virasoro algebra, then the asymptotic density of states is given by this universal formula, which only depends on the central charge. So that's why the universality comes in, that you do not need to know any low-lying spectrum or any other parameter. This formula just holds if you have the central charge. So there are similar looking formula also exist in higher dimension, where basically you use some sort of thermal EFT. It started with this paper by Siraj and company, and then there is a reincarnation of these ideas in this recent paper by Hiroshi, David, Nathan, and Jeha. And there also the idea is that the high energy density of states will depend on very small few parameters of the CFT. If you know those small few number of parameters, you know how the average density of states look like at very high energy.
Ask you this question.
Yeah.
It's not enough to say that this is the asymptotic behavior. What is the error on that formula?
Yes, so that's what I am going to talk about.
Sorry.
That's my favorite. So the first time I learned about this formula, that's precisely the question I asked. Like, what the hell is going on with this formula? Yeah, but so of course, Cardy formula. So one way of saying this, that the density of states is a distribution you are approximating with a smooth function. Though, so this formula as written doesn't make any sense mathematically. Another way of saying the same thing is that the Cardy formula is basically a continuous approximation of distribution, and you want to know how good approximation it is. So for example, like as a starter, this formula cannot distinguish between these three scenarios, because it could have been the case that this formula is only valid when you integrate over from 0 to capital delta, which is a very, very large window. And if that is the case, then the first possibility is allowed, because you just integrate from here to, this doesn't move much, here to somewhere very large delta, and then only this integrated density of states follow the Cardy formula. In the same way, like the second and the third possibility is also allowed. So the Cardy formula cannot distinguish between all these scenarios. Yeah. Yeah, but it could have been the case that this formula is only valid when you integrate from 0 to capital delta.
Delta, that's what it's telling us.
Yeah. Yeah.
That's not what it's telling.
No. So yeah. So this formula, you need to average over some window to make sense of this formula. And suppose the true statement is only when you average from 0 to capital delta, this formula is true. And if you average over any small window, this formula is not true.
Then I think you could tell us that it is going to get more and more states at the time. Because even this average is increasing as you increase the window, right? So that means.
Yeah, but then it cannot distinguish between these three scenarios, right? Because you are only mentioning that how many states are there when you count all the states from 0 to capital delta.
Yeah, but so I know that for this, then for the next delta, I also know that from the formula. So I can effectively know what happened as a change delta.
No. Then basically, so then you are playing this game that you are subtracting f of delta plus something minus f of delta. And you are trusting that formula. But to trust that formula, you need to know the error of the f of delta very well. So suppose you do the thing you said, f of delta plus k or f of delta plus 1 minus f of delta, you get some expression. This expression would be subleading compared to f of delta, some derivative kind of thing. But in the original formula, suppose the error of f of delta is bigger than this, then the subtraction doesn't mean anything.
basically to the extent that, this is tied to Cardi and everything.
Mhm.
I think that, okay, this tells us about, okay, slightly integrated, but a row of delta within a window,
Mhm.
so if I thought in terms of temperature,
Mhm.
you put
Mhm.
the system on a box of size 1, which
Mhm.
is what you said you're doing,
Mhm.
then it tells us about the density of states, in a window of energies of order 1, out of the size of the box, because that's what you coarse grain in thermodynamics, right? Wouldn't you
Yeah,
say
but
that?
in the thermodynamics, isn't it the case the size of the window goes like square root of the energy?
It goes like square.
I would have thought.
Fluctuations go like that, but the density of states. Okay, anyway, let me not divert you. I thought
Yeah, but then I guess, okay, even if I grant you that in the thermodynamics it goes like that, that requires a proof. I mean, because because you want to say that in some sense the microcanonical and the canonical ensembles are equivalent. So that's what we are basically doing. We are basically proving these two ensembles are equivalent.
all of these fluctuations.
Yeah.
Specific heat will tell you.
Yeah, exactly.
How
Yeah.
many-
Yeah.
Maybe you will not be able to say very precise things, but
Hmm.
as far as the distinguishing between these scenarios is concerned, that I thought. But okay, it doesn't matter.
Yeah, but I guess you can do only if you have, so suppose you have this formula and then you have an error term and you have to have a very precise control over the error term. Only then you can do this subtraction business. I am saying that you need to figure that out. So at this point, when someone gives you this formula, the first question you ask, what is the averaging window I need to average over? And all I'm saying at this point, anything can happen. And you need to show that which possibility is okay. So as I said that we want to like a refined answer to this question, we want to distinguish between this scenario in a very precise way. So a natural premise is to consider two-dimensional conformal field theory, which I will focus on. So these are the basic assumptions. We will take central charge bigger than 1, which basically makes sure that there are infinite number of Virasoro primaries. So it makes sense to talk about the asymptotic growth. I will assume unitarity, the modular invariance is there. And I will also assume the vacuum exists. So there is a 0, 0 state. Well, you can cook up a theory which is non-unitary.
Non-unitary. Suppose it's unitary and modular invariant. But you still have to assume that the vacuum exists.
Yeah, otherwise Liouville is there.
Unitary.
Is unitary, doesn't have a vacuum and it has a continuous spectra. Yeah, the identity operator is not allowed because yeah, I think my guess is like in the Liouville, if you do that and compute the norm probably blows up in that case. Yeah. And also the point is if you try to write down a continuous, so Liouville spectrum only has support on 0 spin. So if you want to write down a modular invariant partition function, then from there you can also show you cannot allow identity to be there. So there is this paper by Scott Collier, Sheehan, and Peter Kravchuk, where they actually show that they basically bootstrap the Liouville. So, but this is a very mild assumption. Like for most of the compact CFTs, yeah. So under these assumptions, we can show the following statement that we take the density of states and we integrate over some small order 1 window, which goes from delta minus little delta to delta plus little delta. So this is a size of twice little delta. And the idea is you take the little delta to be some order 1 fixed number and you take capital delta to infinity. And the statement is if you do this, then the Cardi formula is true in the following sense. So here you look at this inequality. Just to refresh your memory, because I have talked about this inequality many times. So for example, if you look at this, the upper bound, so numerator contains the number of counts the number of states in that window, and the denominator is rho 0 delta, which is basically the Cardy formula, which gives you the average density. So roughly speaking, you would imagine that this count versus average density will give you the size of the window. And indeed, you can precisely show that this thing is upper bounded by twice little delta, which is the size of the window, plus 1. And in the similar way, you can put a lower bound in the delta going to infinity limit, where it is twice delta, twice little delta, minus 1.
And now here we are taking little delta fixed and capital delta to go.
Yeah, yeah.
And does little delta become as small as 1 over capital delta? No.
No, in this case, it's fixed. You can make it as small
as you like.
Yeah, but then the lower bound will become trivial, because if you take twice delta to be less than 1, then it's a negative number. It doesn't tell you anything. It could be 0 also. And precisely running this argument, you can put a bound on the spacing. So you basically say that, let me choose a window which has a size which is slightly bigger than 1. That means the lower bound is positive, which immediately tells that this ratio has to be positive. And that immediately means there has to be a state in any window size of slightly bigger than 1. And that basically means the spacing has to be less than equals 1 as you take to large delta. So this was first conjectured in this paper by Bauer and Sasha, and then later proven in these two papers.
Yeah.
So the upper bound basically in some sense tells you that at any single point, you cannot have more than Cardy number of states.
So, like 1.
Yeah, even you can, for the upper bound, you can take little delta to 0, for example. The upper bound is still valid. So that basically in some sense tells you as you shrink the window,
Small window.
Yeah, you cannot
be bigger than the Cardy.
Yeah.
Arbitrary.
Yes. So the Cardy is like that's the maximum number of states that you can allow to have on a single point. Yeah. Oh, okay. Someone asked this. Good. So the lim sup and lim in appears because these limits might not converge, so it can oscillate. But the point is that whatever the limit does is always upper bounded by this number. So that means the lim sup is upper bounded by number. So the proper way to write this is lim sup. Same way for the lim in, because the limit might not exist. And in the same way, the spacing can be arbitrary sequence of some numbers, but the lim sup is bounded by 1.
Even though there might be oscillations, you take the maximum values.
Yeah,
for
yeah,
the sup, and
yeah.
that converges to
Yeah.
which is already bounded by.
Yeah. So basically, you consider all convergent subsequence and take the maximum of that. I mean, there's a definition of lim sup. Yeah. Lower bound on what? That's the lower bound here on this side.
Get that, say delta equal to 1.
Twice delta is just bigger than 1. Then it's a positive now.
I follow from that first inequality.
Oh, so if you just take a window size which is slightly bigger than 1, say 1 plus epsilon.
Delta equal to half.
Yeah, delta equals slightly bigger than half. So that is some positive number, epsilon. So there has to be some state in the slightly bigger than 1. So that means you cannot have. No. So that means there doesn't exist any unitary modular invariant 2D CFT with sparser asymptotic spectra than sparser than 1, basically. So there cannot be bigger holes. Well, individually there can be bigger holes, but you cannot keep adding bigger holes in the spectrum up to infinity. No, it's just delta going to infinity. It happens for every CFT with the central charge bigger than 1. Yeah.
Finite delta, something said about this.
For finite delta, if you want to make some statement, you have to keep track of all the error terms over there. And then you can do actually numerics. So you can plot things and see what are the stuff. Yeah. But whenever you want to make any statement about finite term, you need to keep track of the error term and how it behaves, because all these formulas will be corrected. Yeah, because in principle, all the estimates are there in the calculation. So you can just plug that in a computer. Okay, so basically what I proved that this first possibility can never happen. You cannot have arbitrarily large gap as the energy goes up because, yeah.
That,
Mhm.
I assume that, let's say the gap is asymptotically
Mhm.
Greater than 1.
Yeah.
Is
Mhm.
there a simpler way of seeing that will create consistency, or?
You mean whether there is an intuitive way to guess that there will be a bound? Not that I know of. So the way the proof works, you can see that the spacing is somewhat related to the recurrence in the spectral form factor, like how it. So you plot z of beta plus it, the absolute value, and you ask where the recurrence happens. So if the spectra is very regular, then the recurrence will happen at t equals twice pi or something like that, some order 1 number. And yeah.
Spectrum, so it's 2 points, Z, Z.
Yeah, Z.
That's what you meant.
Yeah.
By recurrence, what do you mean? It goes up and it saturates in some plateau-like form?
No. So that's for the, so think about, so not for chaotic theories, think about Ising model or some integrable thing. So there will be recurrence,
I
right?
see.
And even for chaotic theories, if you do not average, then there will be at some point there has to be recurrence
Function of time.
as a function of time.
Okay, yes.
And the statement, the intuition is that the spacing is related to somewhat this inverse recurrence and things like that, at least for integrable theories. And this fact that there is a bound 1 is related to the fact that the least possible recurrence can happen when like if you plot z of beta plus it, then the least amount of recurrence can happen at t equals twice pi and things like that. So that's the rough intuition. That's basically, if you look at the computation, at the end of the day, so what you are doing, you are basically finding the density of states, which is basically an inverse Laplace of the partition function. And inverse Laplace of the partition function is taking z of beta plus it and integral over t. So in that sense, you are probing the spectral form factor and integrating over the spectral form factor. And then you want to say that the t equals 0 gives you the Cardy formula, and the other part of the integral doesn't spoil the Cardy formula. So you want to avoid, so in that t integral, you want to avoid the recurrence as much as you can. So the second case is just regularly spaced. No, the spacing is less than equals 1. So that was the statement. That was the statement before. Oh, yeah. So you can. So it also says that it can be regular spectra, but the gap cannot be bigger than 1. So the second possibility is allowed, but only in the restricted sense that the regular gap is less than 1. In the usual Cardy formula? Yeah. Modular in the modular invariance, there is a vacuum and there is a gap above the vacuum. So it's a compact CFT. So and unitarity. Yeah. The same assumption. Yeah, there is no extra physics assumption. So the physics inputs are all same. Just so in the usual Cardy formula, what you do, you go to the dual channel, you take the vacuum and you do an inverse Laplace, and then you forget about all the non-vacuum terms. And you say each of the non-vacuum terms are suppressed, but the point is there are infinite number of them and there can be a resummation effect. And this resummation effect is basically capturing the size of the window. So that's the rough idea.
Actually, as you said, crystal spectrum was allowed.
Yeah.
By Cardy formula.
Yeah.
Not actually, it didn't seem like if you just interpret that.
Yeah.
Naively,
Yeah, exactly. Yes, exactly. Yeah.
Okay, levels include that possible.
Yeah. Yeah.
You cannot.
Yeah. Exactly. Yeah. Yeah.
So I mean, as you said in the next slide, so that the equidistant spectrum, for example, was allowed.
Yeah, well, not as long as the spacing is.
Yeah. In fact, there are examples like monster CFT.
Yeah.
Yeah, any rational conformal field theory, basically. Asymptotically, yeah. But all the examples we know is, for example, all the rational conformal field theories or monster, there the spectrum is either regular or there are like finite number of sets, and each set there is some regularity.
Class of theory is regular, and you kind of put an assumption to exclude that, get a better lower bound.
Yes, so that's what we are going to do. Yes. So the question is, can we capture the final option somehow?
Valid for the first, which assumption is not valid for the first.
So you can, so we listed out bunch of conditions, and you can break any one of them basically. And the point is that we do not know any CFT for, so the assumptions I put in, those are basically almost by definition, all the CFTs satisfy that. So there exists no CFTs for which this happens. Okay, so now the question is, can we capture the third possibility for some class of CFTs? And this was supposed to be the chaotic ones where the spacing actually goes to 0. And yeah, and we'll show that in the large, so here we are talking about large energy, but we'll show that in this class of CFTs, instead of large energy, if you simultaneously take large energy and large spin, in some precise sense, the spacing really goes to 0. So what are this class of CFTs? So beyond the usual assumptions, no, I will rule out these integrable theories by putting this extra assumption. No, not the sparseness. I haven't yet made. So this one, the twist gap. Yeah. So this is my certain class of CFTs where, and so naively you would think that if I am probing chaotic CFTs, then there better be no other symmetries other than Virasoro. So natural choice is to impose no symmetry beyond Virasoro. So in terms of spectra, it basically means there is a twist gap in the spectra of Virasoro primaries, and twist, to remind you, is delta minus J, which is in terms of H and H bar is twice minimum of H comma H bar. So there is a state which is 0 comma 0, and then all the other states with H comma H bar has some gap. So there is no H comma 0 or 0 comma H bar states.
You say something about how big the gap should be.
You can show that, you can actually prove that the T gap cannot be bigger than C minus 1/24. So you cannot make this. So there are these two lines. It cannot be the case. There's nothing here. So that thing you can prove. But other than that, as long as it is positive, everything I'm going to show you goes through. No chiral opera, no higher spin currents.
So that's all you're assuming.
Yeah.
No symmetries, basically.
Yeah, exactly. No symmetries beyond Virasoro. Yeah, exactly. Kashmir is also not allowed. Yeah. And I will be using this picture again and again just to orient you. So H and H bar are the left movers and the right mover weights. And there are two special lines, which is C minus 1/24, which will play some role. We'll see. And in this diagram, you can see some diagonal lines which goes along 45 degrees. Those are basically fixed spin lines. So as you go like this, you are increasing the spin. And in this sense, you are decreasing the spin. Okay. So to recap, we consider central charge bigger than 1, unitary, modular, invariance, vacuum. So all the first 4 conditions are very natural, and the final condition just says that we only consider CFTs with only Virasoro. Okay. Now what can we do with this? So now I will give you the flavor of results we can derive. So first of all, as I am saying that universality in the large spin at a fixed central charge. So in some appropriate sense, we will show that the large spin spectrum is dense. And here by large spin, basically you fix H, you increase the H bar, so spin increases, or you fix H bar and increase the H, so spin also increases. And we'll show that there is some universal growth along this direction and along also this direction. And it doesn't really depend on the size of the shaded strip. And I'll be more precise. What do you mean by current?
Just interested in that delta, the previous
Yeah.
setup with the
Yeah.
partition.
Mm-hmm.
And I want hope delta
Mhm.
lower bound.
Yes, yes.
That's just slicing it this way.
Yes, yes.
So if you have a universal growth, this two directions, then presumably, even if you move kind of diagonally, you will see that.
Yeah, but you can, for example, yeah, you can probe that kind of regime, but you have to be a bit more careful. For example, if you say I will be looking at fixed spin large delta, then you cannot
No,
fix.
you just get large delta.
If
The way Faraday, basically Faraday.
yeah, if you just look at if you look at large delta and large spin, then you can transfer this result in the
Large delta.
yes. Mm-hmm.
Row of delta, let's say I'm interested in the way you were before.
Mm-hmm, mm-hmm.
Now, given that there is this gap, can you say more?
Oh, in that sector, no, no. As of now, no.
But why not? Because as you said, this way there's universal growth, this way is universal.
Yeah, but here the spin goes to infinity.
Yeah, now, so you just move this delta, just this slice moving this way, right? Correct.
Yeah, but oh, so you do not want to do fixed spin. You just want, oh, I see. Sum over all spins.
Just having interest.
Yeah, you can do that. I would think so. Yes,
That
yeah.
Kind of tie nice.
Yeah, yes. I think you can do that.
Your
Yeah.
one will become.
Some delta to the power minus 1/4, something like that. It goes to 0 basically. Yeah. But I think the holy grail would be to prove it for each fixed spin line. Like that's what people expect. Yeah, that's really, really challenging. But yeah, we are making progress. So maybe I don't know.
So the spin line will take you
The these diagonal lines. So the one you are thinking about, you are basically slicing over the whole thing. Yeah, in that case, you can easily translate, as you said. Yes, indeed.
That will just then, the cardiac symptoms will be universal then.
Yeah. So for example, the setup you suggested there, the result would be the spacing actually goes to 0 as delta to the power minus 1/4 plus epsilon, at least as fast as that.
How does it compare to the upper bound? Is it close to that?
Upper.
The rho naught of delta.
Oh no, rho in terms of like if you people expect that the rho naught delta goes like exponential.
This will not. The lower bound will not be exponential.
The lower bound on the spacing, you mean?
Yeah, lower bound on the density of state in some window. I'm just trying to see what you have in the previous time.
Yeah, definitely. Okay, sorry. In the previous language, if you take density of states and you integrate over some small window, then I think the lower bound would be exponentially large. But you have to be a bit more careful when you say, so you have to take the density of states and integrate over this very narrow window. So after integrating, it might not be exponentially large or whatever the answer would be. But the point is you can take the density of states and integrate over very small window where the window goes to 0. But somehow it's more natural to think about in this H and H bar variable because you will see why it's more natural. Yeah, exactly.
Connect.
Yeah. So let us explain the results a bit better. So basically you take any strip on the H variable. And this strip can be put anywhere on this axis and you fix the size. Then you consider these fixed spin lines. And then the idea is to count the states which are on these fixed spin lines and also lie on this green strip. So you basically count number of states in this black strip, then on this black strip, and then you go up like this. And you want to know, as you go up, whether this counts satisfy some Cardi-like formula or not. And the precise statement is following. So in the numerator, you basically count the number of states on these black strips, and you go, and j going to infinity is like going up. And so roughly you would think that this formula should depend on two variables, h and h bar, like, or j and h, because it's a two variable density. And as you go up, because the spin is going up, becoming large, you would expect there is a Cardi-like factor for the spin. So this is this factor here, in the denominator. And the statement is that if you take a ratio and take j going to infinity, is given by this precise formula here, which is some rho 0 h integrated over this green strip, like over this region omega in the h variable. And this rho 0 h is given by this cosine hyperbolic. So it's a precise formula. And one of the important point is that it has only support over h bigger than a, and a is this c minus 1 over 24 threshold. Oh, so a is basically c minus 1 over 24. So I haven't explained you how this formula comes about, but this formula comes about, you take the vacuum in the dual channel and do some inverse Laplace, and this inverse Laplace only has support over a. So that's where this formula is coming from. And it also tells you something, like I will explain how it also tells you something important, whether you are above the threshold or below the threshold, like this c minus 1 over 24.
Why didn't you take windows and j? The way you did for delta.
Oh, because we know the j's are integers, so we do not.
So it's different about a particular j.
Yes, yeah, exactly. So that's a big advantage here, because we can use that we are using bosonic CFT and there is a T invariance, so j is integers. So unlike earlier, I need to smear over delta, but here I do not need to smear over j. I only need to smear over h, because I can use the fact that j is an integer.
We know rho of j of delta.
We know rho. No, we don't. We don't know that. Yes, that's the CFT. So that integral is really a discrete distribution. I haven't really explained you. So at the end of my talk, I don't know how much time we'll have, but you can bug me later if I do not get time. So how we derive this formula?
I'm not able to process the completely. I'm so sorry.
Yeah, sure.
The green begin to be order 1.
Yes. Yes.
What is this telling me about rho j as a function of as the asymptotic?
Yeah, so it basically tells you that the asymptotically, you are taking h bar variable to be very, very large. So you would expect there is a Cardi-like growth in the h bar variable with some prefactor which depends on h. So this is the Cardi-like growth sitting here in the denominator, and the prefactor is precisely this integral. Yeah.
How small is that?
Right now, the way I have shown you, it can be any order 1 number, but you can take it to be as small as you want. You can take it to be 10 to the power minus billion if you want.
Just held fixed in the limit.
Yeah, held fixed. At this point, it is held fixed, but later I will improve.
Can this window overlap with something less than 3?
Exactly. So that's a very good question. If the window is below the threshold, then basically the right-hand side is 0. And that basically means that if you are below the threshold, then even when you take h bar going to infinity, the growth is less than what you would have naively predicted from Cardi.
What is this threshold say?
So this integral has a support which is h greater than a. So a is c minus 1 over 24. That's the BTC threshold.
Yes.
So if your green strip is below the threshold, then this integral just is 0. And that basically means the growth is always slower than the Cardy growth. So if you are below the threshold, then even if you take h bar going to infinity, the growth is not Cardy growth, rather it's sub-Cardy.
The window as part of it.
Then you just do the integral and whatever comes out. You just forget about the part that is below the threshold. Yeah.
You don't assume anything about sparseness or anything.
No, exactly. Yeah. 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 So it basically shows that if you extend it to the large central charge, I strongly believe that there would be some result like this. And then which would be in line with the fact that there is no BTZ black hole below the threshold. Here, the size of the window can be anything you want. It can, so at this point, it cannot be J dependent, but it can be any number you want. You can make this number as small, as big, whatever your favorite number, real number.
Sridip, I have a question.
Yes.
So this threshold is when the black hole becomes extremal or something?
Yes, the threshold is where the black hole becomes extremal. Exactly.
Okay.
The extremal limit seems very interesting.
Yeah,
Right.
indeed. Yeah, and earlier I was complaining to you that we only have results for grand canonical, not for canonical, and I think now we can probably do the canonical, extending this result. I haven't tried, but no.
For example, take it symmetry, you can show that the gap is.
For the supersymmetric, you need to, there would be more symmetries. So then you need to be more careful about how you handle these limits. So the ideally you can play this similar kind of conceptually similar kind of game with extra symmetry, but then you have to impose some twist gap condition with respect to the bigger symmetry, and then basically redo.
There is some large density of states at the threshold, right?
Yeah, in the super.
Then the gap.
Yes.
That,
Yes, yeah, absolutely. Yeah. And I think, if one can redo this analysis with supersymmetric characters, then one should be able to prove that. Okay. Yeah.
I'm sorry, so sounds reasonable just to ask. I know that statement about, a large number of states and then a gap in S1, A, and so on. But is it a established pattern for symmetry? I'm just asking that.
I thought that the consequence of this real world is
Yeah. Yeah, I think there are papers by Luca, Joaquin, all these people. And yeah.
Just from the near-horizon analysis. Symmetric S5, whatever. I mean, J, it should be symmetric J, just from there. Okay, yes. Sounds right. Okay, you're right. Yes.
Yeah, so I would imagine that instead of rho 0, you will have a different function, and this different function will have this property that it has support on one point, and then there is a continuum gap, and then there is a continuum. So this function will change rho 0.
Also tell me about this spin, which is an extra data.
Mm-hmm.
Instead of skin,
Yeah, I think these are all should be tied with the near extremal geometry and so on. So yeah, I think people. So as far as I know, Joaquin and Luca, these people have looked at the vacuum character in this supersymmetric setup, and they do an inverse Laplace, and then they get this thing. But then you need to control the non-vacuum terms also to make sure that this formula is not wrong, and what is the regime of validity, and so on. And
And
that's not been done. Yeah. Okay, so once we absorb this formula, we go ahead And as I said that the RHS is non-zero if the strip is above the threshold. And the RHS is 0 if the strip is below the threshold. So the growth below the threshold is strictly slower. Hmm.
Growth is slower because that's just coefficient, right? The growth is still that J dependent function.
No, the coefficient is 0.
It's 0, but I mean, it's not exactly 0, is it?
No, it's exactly 0. That's the
Then
formula
why
tells.
is it slower? You just say there are no states.
No. It could be, so it could be 1 over J on this side. Yeah,
Yes.
yeah.
Yeah,
yeah.
Without putting in supersymmetry or,
Mhm.
you know, all kinds of situations, in the grand canonical ensemble,
Mhm.
you folks established precisely
Mhm.
and the black
Mhm.
hole, etc.
Mhm.
But if you did it with supersymmetry,
Mhm.
could you, in the grand canonical sense, at least see the nature of the spectrum?
Yeah, presumably yes, but one probably needs to work a bit hard than what. Yeah, definitely.
Getting my skin. I'm sorry.
Where is Indranil? I don't see him.
Various technical reasons which Sridip will explain later on. They can do the analysis where they, instead of working with the energy and J, they go to the beta. You know,
Beta left and beta right.
Okay, right? For physicists like me. So that's all I'm saying. Do what you have been saying, right? And also gainfully employ my student. Okay, afterwards, yeah.
Okay.
This line from
Oh, that's the so from the bulk point of view, this is the BTD threshold. So below the threshold, you would not expect any black hole to be there. So you would expect the growth is slower than the black hole growth, which is the Cardi formula. So that's the intuition. But this result, as I show you, is not applicable in the large central charge limit. Like we haven't extended the regime to the. Yeah. Oh, why the number is C minus 1 over 24? I think this is related to the fact that the mass of the black hole becomes 0 as you hit the threshold. And below the threshold, if you write down the metric, then it becomes a conical defect. So there is no horizon. And the mass is related to the central charge because of ADS CFT. The central charge is related to 1 over G Newton and so on. Okay. So this I have already mentioned that the RHS is non-zero irrespective of the width of the strip. So you can take it any. And this immediately tells you that the maximum spacing of states with a fixed spin J has to go to 0 as J becomes large, just from this result. It doesn't yet tell you that how it goes to 0, but it immediately tells you it goes to 0. And I can show you by some simple argument. So how do we show this? We show that, so suppose this size is twice delta, the size is delta, the size of green strip. And we can show that the spacing is less than twice delta over capital N for any n greater than 0. And that amounts to showing that the spacing indeed goes to 0. So to show this, we do the following trick. So here I take the strip and I divide into 3 equal pieces. So instead of 3, you can do it for n pieces. And so this is my original formula here. But now I can apply this original formula on each of these sub intervals. So omega 1, omega 2, and omega 3. And because this limit is given by this cursor is very annoying. Because this limit is given by, yeah, maybe I'll use the stick. It's I feel like the cursor is out of my control. Yes. Okay, great. So you have this thing here. So it basically means if you take J to be very large, then this number becomes bigger than half times whatever the asymptote is, right? Because as you approach the limit, after some point, you will be inside this band. So that means for each of these interval, omega 1, omega 2, and omega 3, you can pick some ji such that for j greater than ji, this thing is greater than 0. And that basically now what you do that instead, so you have 3 ji's, so now you pick the maximum ji. And the point is that beyond this maximum ji, each of these subintervals has to contain positive number of states, right? And because each of these subinterval has to positive number of states, that means the maximum spacing would be the twice of this size. So one state can be here and one state can be here. So the gap is twice delta over n. So in this case, the gap is twice delta over 3 in this picture.
So now you're talking about spacing.
Yes. So okay, maybe I should. I can go back. So the statement was that I want to show that the maximum spacing goes to 0 in this direction. So what does it mean to show the maximum spacing goes to 0? It basically means, so suppose this is delta, this size. We want to show the spacing is less than twice delta over capital N for any n greater than 0. If you can show this, then we are done. The spacing goes to 0. And the trick is very simple. So you take this window and you divide it into n equal pieces. So here n equals 3. So I have delta over 3, delta over 3, delta over 3. And for each of these subinterval, the asymptotic is true. So basically you apply this thing. So it basically makes sure in each of these subintervals, you can pick a ji such that if spin is bigger than ji, then there exists positive number of states in each of these subintervals. And then you pick the maximum ji, and because each of these subintervals beyond this maximum ji has finite number of states, the spacing can be as big as this much, which is twice delta over n.
So once you're above the GI, it's always
Exactly. But here, it's very crucial that this n is finite, because you want to pick the maximum gi. So later when I will, so this argument will never tell you how fast it goes to 0 as a function of j. It can only tell you that it goes to 0. So we need to do some refined analysis to get to that answer. At this point, no. So at this point, you run this argument for every finite n. And of course, if you increase n, then presumably you have to go higher and higher up to see the effect. Okay. And so I already told you the maximum spacing of states with a fixed spin j goes to 0. And there's one more point I want to emphasize, that because here the prefactor is completely fixed, if the strip is above the threshold, that basically means the entropy is universal up to order 1 in j, which is very different from usual Cardy formula. In the usual Cardy formula, the entropy, you have a square root delta, you have a log term, and then the order 1 term is not universal. It depends on how you are averaging. But because here you do not need to average in j, and you precisely know the factor that coming from averaging over h, so that means entropy is completely determined up to order 1 in j. So you have more predictability. Okay. So now, roughly speaking, we have learned that the density of states in this direction, there is a Cardy growth and there is a precise prefactor. But now what we want to ask, how does the error behave, or how the limit is approached? And the point is that if we can prove how the limit is approached, you can basically say that the spacing goes to 0 as some particular function of j. So we want to know how does the error behave, and we also want to know whether we can shrink the window size as a function of j. So earlier we were always dealing with a fixed window. Okay. So do that. What we do the following thing. So here, So first of all, we basically smoothen things a bit to estimate the error. So we introduce this phi function, which is compactly supported. So this phi function has a support only over this green strip. And this is a smooth function. And for example, you can consider any kind of bump function, which is a smooth function and compactly supported. And this is your, so I rewritten rho j delta prime in this variable. So this is your full density of states, the actual density of states. And this formula comes from some contribution from the vacuum module. So I have rewritten this leading term as rho j vac. And this difference is basically the error term. So I take the error and I smoothen it out with this phi function. And then I divide by the leading growth. So this quantity basically computes the relative error with respect to the leading term. And you want to show that this relative error goes to 0 in some appropriate way. So is the setup clear? Just make sure.
So what is within the brackets? It's rho j of that.
So rho j is the full density, and this one is basically this term. I have rewritten in this abstract way. So another way of saying things is rho j vac is the inverse Laplace of the vacuum term. So whatever you get. Vacuum in the dual channel. Yeah. So the point is that we know what rho j vac is explicitly, and that's the difference. And I smooth it out with this phi, so smoothing is also very important. We'll see. So now the next question is that, so can we let delta to go to 0 as a function of j, and how fast can we do it? Like whether we can shrink the window. So here I'm just showing you the result without explaining how to derive it. And if time permits, I will explain a bit later. But the point is that this thing, you can estimate it with this factor here. And then you see that if you choose your delta to be j to the power minus 1/4 plus epsilon, then you can make this go down by any power of j. And here the crucial input is that because you are choosing a compactly supported smooth function, in the Fourier domain, this function has a fall off which is faster than any polynomial fall off. And you use that fact to your advantage. So here this number n or this number p can be any n or any p. It basically says that the error goes to 0 if you make sure the window size is like not smaller than j to the power minus 1/4 plus epsilon. The error goes to 0 faster than any polynomial. So in some sense, that if you take your Cardy formula and smoothen it out with this compactly supported smooth function, then it is true up to any polynomial correction. So which is a huge regime of validity than the usual Cardy formula. Yeah.
When talking about density of states at a particular value of j? No, sorry.
Yeah, it's the same thing. You count the density of states and you integrate over this window. Earlier you were counting the number of states, but now instead of counting, you basically smoothen it out by this function. And then you basically take j going to infinity limit. And the statement is that as j goes to infinity limit, this error term goes to 0 faster than any polynomial, as long as the window size doesn't shrink like faster than j to the power minus 1/4 plus epsilon. Oh, that basically means that the Cardy formula is basically coming from rho j vac, right? Because that's this piece.
That's what called Cardy.
Yeah.
That is j from data.
Yeah. This whole thing is like the Cardy formula. So the statement is that if you take your actual density of states integrate over the integrate, smoothen it out with a compactly supported thing. This is your Cardy formula. You smoothen it out with a compactly supported thing, and then you ask what is the relative error between these two terms. And I'm saying this relative error is faster, goes to 0 faster than any polynomial. So in some sense, in this case, the Cardy formula, when integrated against this compactly supported smooth function, is true at any order in any polynomial in J. So it's, and yeah, this will lead to a result how the spacing goes to 0, but not yet. I will come to that.
The window size
Is
big as G.
yeah, basically you can see from here. So you want this term to go, you want this term to be very big so that this goes to 0. So yes, that's why that means if you make delta to be very small, then that will spoil things. So the best you can do is that you can do j to the power minus 1/4 plus epsilon. That will kill this j to the power 1/4, and there will be remaining j to the power epsilon, and that will make sure that it goes down. That's good enough.
So you can't make the window too small in terms of J.
Yeah.
Then
Yeah.
it's-
Yeah.
Regardless of the smoothing function itself, as long as it's something.
Yeah. So this, yes. So the point is that, yes. So if you make this window, then the Cardy formula is true up to any order in 1/J, basically. What function is constant? But it cannot be, then it's not smooth anymore, because any constant function compactly supported, you have to have a jump, cliff. You cannot allow a cliff. And that's why I said the microcanonical entropy is universal up to order 1 in J. Because for the microcanonical entropy, you need to have a cliff. It's a constant function and there is a jump. Yes, so the statement is in the Fourier domain, this has a fall off which is faster than any polynomial. So n can be any number, any integer you pick. And instead of smooth, if you choose some Cn function, instead of C infinity, if you choose some Cn, then that n is related to this n, I think. Yes, you were saying something.
By doing this, putting the envelope inside the cliff and outside the cliff and so on, right?
Yes, you can do that, yeah. But then you basically, like, you take some limit by doing this approximation, and then you lose something by taking that limit. And that spot, so here you have all orders in J, and by taking that limit, you can only control up to j to the power 0. So you lose something there. Yeah, one more comment is, if you do not care about compactly supported function, suppose you take your Cardy formula and integrate against some Gaussian function, which basically leaks out. Then I think you can show that the Cardy formula is valid up to exponentially suppressed correction. But then it's a trade-off, because then you are letting it leak away from your interval. So it's not really any kind of microcanonical setup anymore. So depends on how you want to use it, I guess. Yeah. Okay, so I said the window size shrinks like this, but this doesn't immediately prove that the spacing goes to 0. So there's a catch, because so you can imagine dividing this interval so that each of the size is j to the power minus 1/4. But now the problem is that as you go up, the number of division goes like j to the power 1/4, which becomes bigger and bigger. So you cannot run the previous argument I showed you. And for that, you need some notion of uniformity, which is basically you show that this estimate, as long as the center of the interval h star is bounded, this estimate is locally uniform. So that basically means, irrespective of wherever you pick this interval, the asymptotic kicks in at the same time. It doesn't matter I sit here, I stand here, or I stand here. The asymptotic kicks in uniformly at the same point. And then you can use the window size to show that indeed the spacing goes to 0, at least as fast as j to the power minus 1/4 plus epsilon. Which one is the assumption? No. We proved it. So sorry, I didn't probably explain. So here you can see there is an order e to the power a star b. So that's the only dependence goes in. So as long as a star is bounded, you can just replace it with some number.
A star was just a parameter.
Yeah, a star is the center of the interval. Yeah.
What you just said about it being uniform.
Yeah.
Is it any smooth function? Like, what does it mean to jump?
Oh no, uniform basically means, so it's basically, think like this. So you have so suppose suppose you divide it into two pieces. So in the first piece, the asymptotic kicks in at J1, and in the second piece, say the asymptotic kicks in at J2. And then you can say that in both intervals, the asymptotic kicks in when I pick the maximum of both. But now I cannot run this argument if I have to divide the interval in the size of j to the power minus 1/4, because then the number of intervals would be j to the power 1/4, which grows bigger and bigger. So I cannot run this argument of picking the maximum. Yes, exactly. Yes, exactly. So it might happen that in some sub interval the spacing goes like j to the power 1/4, but in the another sub interval which is adjacent to this, it kicks in some at later point. Yeah, but then I have to make a statement about the whole interval, right?
So intervals that.
Yeah, yes, exactly. There are so many intervals that you cannot run this argument. In other words, it can be the case that, yeah, it can be the case that suppose these are your fixed spin lines. The spacing is like j to the power 1/4 on this side, but on this side maybe the spacing is very large, and you cannot make any statement because the asymptotic kicks in on this side much later, and you do not want to allow that possibility. Yeah, this is a very subtle point, but yeah, we had to spend 1 week to make sure that this works. Is there any question? Oh, so you want to show that this error term, so you want to show this error term doesn't blow up as you basically go, as you move things, slide things around. Yeah. So the point is, as long as a star is bounded, you are through. Basically, you can bound it by some number and you can forget about it. But that basically means you cannot take you cannot let a star to be very, very large. Then you will be, so there could be possible. So what we say that the spacing goes to 0 in any bounded interval in twist. But if you make the interval in twist unbounded, then the result is not there.
That window you
have. Yeah. So that's why I said local uniform. So that's the local part of the local uniform. It says uniform as long as a star is bounded. Because it could be if you let a star go to infinity, then you see it blows up. So you cannot allow that to happen. So yeah, I haven't really explained. Beta is some particular parameter, which is fixed. You fix some order 1 number. That's it. Yeah. Yeah, I should have explained. Yeah, I think this just comes from the analysis. How much time do I have? I think I have explained all the main results. Okay, then I can probably finish by 1. Yeah, great. That's the best part of giving talks here. Okay, great. So I already said this in the maximum space. So basically we captured this scenario. It's not quite large energy, but large spin and bounded twist. Okay, now I will give you some intuitions behind this proof and sketch the derivation a little bit more. So So of course, we all know that we start with a partition function, and there is a modular invariance, which tells us that you change beta L to 4 pi square over beta L and beta R to 4 pi square over beta R. The partition function remains same. And then you can use the fact that the central charge is bigger than 1, so there is no null states in the non-trivial Virasoro primaries. So you can divide by the Dedekind eta, and you can write down a partition function only for primaries. So these are all the non-trivial primaries, and this is contribution from the vacuum state, and these two factors are there because there are null states in the vacuum module related to the fact that L minus and L plus annihilates the vacuum. Yes, exactly. Oh, the twist gap is used only here, that all these primaries starts with some T gap.
Fact that only character is the multiplication by Dedekind.
Oh, that is true only also for any C greater than 1. As long as C is.
So this gap 0, then you would have no state.
Yeah, then you would have more terms here.
Yeah.
Yeah, but you can write those terms.
So this is not where your assumption is. Because as you said, you could
Yeah, here in some sense I already used that, because if there are 0H or H0 states, then I would have written another term, and those terms will be supplemented with one of these factors.
Yeah, I understand, but I was wondering, is this why you needed that risk gap to 0, that you don't want to write those terms?
Yes, yes, I do not want H comma 0 or 0 comma H in my setup. Because
if you had those additional terms, your argument wouldn't work.
no, then the vacuum term will. So the point is, you take beta R going to 0 limit, and then you have to consider what states contribute. So in the beta R going to 0 limit, all in the dual channel, all the states will contribute which has H bar equals 0, and you want only the vacuum to be the one that contributes.
Let's say I have control over that. Right?
Yeah, then you can.
Then I can
Yes, absolutely.
do,
Absolutely, yes, absolutely. Yeah, as long as you have control over what kind of zero twist state you have, you can do the analysis.
You can do that in a controlled way.
Yeah, you have to know how many zero twist states are there. Then the leading answer will of course change, because those zero twist state will contribute.
You say, okay,
Yeah.
symmetry, but you have.
Yeah.
You can repeat.
Yeah. So, yeah, in fact, Jaishin and I had some estimate in this setup in the near extremal limit in our previous paper, not for the whole thing. So some version of this result were already there in the near extremal limit, but now we can put the green strip anywhere and make the near extremal limit much better also.
if you do the chiral algebra, you can improve the system.
Yeah, as long as you can, so that on the, well, in conceptually, yes, but yeah, you have to have some control over. Yeah. Then, yeah, presumably you can do that. Yeah. But then I guess if you have a chiral algebra, probably more interesting question is to ask what happens to the chiral primaries, not the Virasoro primaries. So probably a natural thing would be impose a twist gap with respect to the bigger chiral algebra and then do an analysis, rather than keeping track of all the twist zero states. But if you keep track of all the twist zero states, then you can make a statement about the Virasoro part of the bigger chiral algebra. Okay. So yeah.
The primaries which have nulls beyond the risk gap, right?
Yes.
That's the algebra, you have all these-
Yes.
those have character.
Yes.
Then you would have to kind of.
Yeah, so you have to make sure you have to play this game. So why? So if you have just Virasoro, then C greater than 1, make sure that there are no null states. So even for Kac-Moody algebra for Wn, if there is a limit on C, and if you take C bigger than that, then that will ensure there are no null states. And that will not be your usual Kac-Moody kind of WZW model kind of thing, because there you always have finite number of primaries. And you do not want that, because you want to talk about asymptotics.
So that So WGW,
Yeah,
where you just have some finite number.
yeah.
Then this is not. very-
Yeah, this is not very interesting, but you can imagine a scenario where you have the same algebra, but central charge is bigger than some threshold value. And then you can, in principle, can have infinite number. Not for the usual WGW models. In the same way, for Virasoro, for C less than 1, you always have finite number of Virasoro primaries. Only for C greater than 1, you have infinite one.
So then if you take your primaries
Mhm.
and write them as representations of the Klasmudi algebra,
Mhm.
then I think you fully have these integrable representations because those are consistent with unitarity.
In the usual WGW model. Oh, in general, I guess, no, not necessarily, because no, I don't think so. Just think about even the Virasoro case. Even for the Virasoro C greater than 1, you would have thought the same thing.
The point, the distance is the Klasmudi one plus some additional.
Yes.
not just the power up.
Yes, exactly. Yes, exactly.
You would get delta corresponding
Yes,
to that,
exactly. Yes,
which would not have the elements.
yes. Okay, so we have, so because of the Dedekind eta, when the modular transformation picks up some extra factor, but you can keep track of this factor, which is 4 pi. So this is the modular crossing equation that we are going to use. So in the usual Carty formula, we just know in the beta going to infinity limit, the vacuum dominates. So you do the modular transformation. So in the beta going to 0 limit, the vacuum of the dual channel dominates. And then the idea is you write down some crossing equation of this form. On this side, the vacuum dominates. And on this side, the high energy state dominates. And you do an inverse Laplace to gain something about these high energy states. That's the usual Carty formula. So here also you play the same game. You want to know, okay, I already told you this. You already know that you want to probe large spin, which basically means either H large or H bar large. So that means either you take beta left to 0 or beta right to 0. One of these options will work. In fact, both of them will work. So let us focus on this case where beta r to 0 goes to 0. So we want to understand this crossing equation in the beta r going to 0 limit. Okay, something happened over there. I don't know what. Okay, so now I'll give you a real quick sketch of the proof. So, yeah.
So you showed us how you got those bounds, etc. Now what are you trying to do? Sorry.
Oh, so I am trying to sketch out the proof of that how it falls. Yeah, the result. Yeah. Yeah, it will be a very quick sketch. Just to give you some flavor. Because at the end of the day, probably one needs to sit down and do it to really. So roughly the idea is to estimate this quantity here, which is the spectral density at some fixed spin. And you integrate over this phi of h, which is some smooth compactly supported function over this green strip, and you want to estimate this quantity. Now, the first thing you want to do to estimate this quantity, you go to the Fourier domain, and that's where this factor beta comes in. So this beta can be any number that you choose, and once you choose, you can fix it. So in the Fourier domain, and you want to go to the Fourier domain because you have knowledge about the partition function. And you want to use the fact that in the beta r going to 0 limit, the partition function is dominated by the vacuum. So a natural thing is to go from this variable to this kind of quantity. And to go from here to here, you can just do a nice Fourier, like the Fourier transform. So this phi of h becomes this function, which is phi tilde of s. And this also becomes a partition function. And then there is an integral over s from minus infinity to plus infinity. So this thing is valid as long as beta has a positive real part, because you want this integral to be finite. Okay. Now, what we need to do, we need to understand this thing in the j going to infinity limit. So now the point is that I know this thing is basically a fixed spin partition function. So when I take the full partition function and I project onto a fixed spin. So this thing can be written down as a partition function and with a Fourier integral, which I wrote it as a contour integral, like and the contour is along the vertical line where real z is this factor, and it ranges from minus pi to plus pi. Sorry, it should be minus I pi to plus I pi in the vertical direction. So this is nothing but a Fourier transform. So basically, and here you use the fact that spins are integers, so this integral goes from in a finite range. And this value is chosen in some particular way so that the non-vacuum, so at the end of the day, you want to show that vacuum dominates and the non-vacuum term goes away. And to do that, you can see later, you can see that this real part of z has to be taken in this particular way. Is there any question at this point? At this point, there is no information. So the information of T gap is hidden here, and then I will use that in a. Yeah. Yes, is the Virasoro partition function. So it only counts the primaries. Yeah. So you take. Yeah. So is the usual partition function. This integral does the projection to spin J. And that goes here, and we want to evaluate this. Okay. Now, as I said, this is this. And then because this is the partition function, I divide it into three pieces. One is the vacuum where h equals h bar equals 0. That immediately gives you the leading Cardy behavior that we all want. And then all we need to do is we need to show that the rest of the term goes away and doesn't contribute to this integral. Now, once you and rest of the things can be divided into two categories. One is above T gap and below A, and the other one is above A. And in both of these cases, when you analyze the behavior of the partition function, you will see that there is an exponential separation. Remember, the leading growth was e power 4 pi square root aj. So this minus tau, which is related to the T gap, will give you some separation here. But then you will also see there is a exponential growing factor with respect to s. So that means that this is good for small s, but bad for large s. So you can, because if the s increases, then this will increase, and this s integral goes from minus infinity to plus infinity. So that means I can only use this estimation. And this estimation just came from modular transformation, using modular transformation in a clever way. But I cannot use this estimation for large enough s, because then this will blow up and this will spoil the estimate. But now, yeah, so the rate piece divided into three pieces: vacuum, then two kinds of non-vacuum. And the vacuum gives you the leading behavior, and you want to show that non-vacuum goes to 0. But then you estimate the non-vacuum contribution. So the first factor is very nice because you see there is this exponential separation. So you are happy. But then you see that with respect to s, this grows. Then you are unhappy because this integral goes from s minus infinity to plus infinity. So somehow you need to manage this. So in other words, you can only use this as long as s is small and bounded. And then for large s, you need to be more clever. So for large s, what you do, you basically use this factor because you know that in large s, this has a very nice polynomial fall off, faster than polynomial fall off. And for this rate factor, you also know that this integral is bounded by its value at s equals 0, because you can just put an absolute value and forget about the s equals 0. So the behavior at large s, this is how you control it. You basically use this blue factor here, and you use and bound the rate factor by its value at s equals 0, and that gives you some polynomial fall off kind of error, and that's the error that goes in the formula. And once you do all these things, you basically land up with the formula that I wrote before. Yeah. This one? Yes, yes, right. Yeah, it still has exponential. You mean this growth? Yeah, it still has exponential growth. But then the point is for large S, this has a fall off in S, in the polynomial fall off. And that polynomial fall off control. So at the end of the day, so let's think about this way. So the leading behavior is exponential. Maybe I should write somewhere. So the leading behavior is, okay, this is. So the leading behavior is this. And you want to show that everything else is suppressed compared to this. So when you have a small s, you can use this estimate and you can use this fact that tau is positive, things are suppressed. For large s, you cannot do this because this will spoil things. But I am saying that after some threshold, instead of using this estimate, you use the fact that this integral is bounded by the value of this integral at s equals 0 times this phi tilde of s, which has a polynomial fall off. And because this has a polynomial fall off, the answer you will get is this times something which falls off in 1 over j. And which basically means that this final bit is also suppressed. If it's not clear, you can also ask me. I mean, okay. Okay. Okay, and so this basically, okay, this basically shows how you prove things, and if you only, so there's one more point, that if you only care about the limiting behavior, not care about the how the limit is approached and so on, then there are other routes to prove the first result I showed you. So, and is the funny thing is that the way we have written the paper, we actually proven the weaker result first, that how the limit is approached, like what the limit is by using some fancy theorems, and then we realized that we can just do this like brute force analysis and estimate for complex beta and prove a stronger result. But just to give you a very quick flavor of the other thing that doesn't appear in the paper because we scrapped it off, I will give you some sense of flavor, a different route if you only care about the limit. And in this case, what you do, you want to estimate this integral here for complex S, and you want to take a large J limit. So initially the large J limit is outside this integral. So you want to basically take the large J limit inside the S integral, and you want to evaluate this. And then so basically this amounts to swapping the integral and the limit, which use the dominated convergence theorem. And you basically show that this integrand can be bounded by its value at s equals 0, just like I said before, because this has a polynomial fall off. And this basically allows you to use the dominated convergence theorem and take the limit from outside to inside. So now you basically need to show that there exists some function zeta, so that xi, such that this limit exists for every yeah.
So you have that product.
Yeah. Yes. Large. Yes.
So to begin with, you want this whole object, and you want to take J to be larger.
Yeah.
And then for using that, you can move that.
Yeah, you can move the limit inside.
That second integral.
Yeah. The reason is there is something called dominated convergence theorem, which basically tells you that when it is allowed to swap the limit and the integral. And the dominant, it basically tells you that you can, so the idea is that you have some stuff and you show that this stuff is bounded by some L1 integrable function. And so here what you do, that you can easily take the integrand and bound it by forgetting about the phase. So it's the value at s equals 0. So now this becomes s independent, so you can pull this out and rest of the things are integrable. So that allows you to use this theorem. And And because it allows you to prove this theorem, you can take the limit inside, and then you just need to show that this limit exists. And then you basically do it into 2 steps. So we would like to know that this limit exists for complex beta plus is. And then the point is that if you know the limit for s equals 0, then there is another fancy theorem which tells you that you also have to know the limit for complex beta, because these are all analytic functions. And the idea is that if some analytic function is locally bounded on some complex domain, then if you know its limit on the real line, you also know its limit on the complex plane. So basically it tells you that if you know this limit, which will be some analytic function, you can immediately know this answer also, just by doing the naive analytic continuation. And this theorem guarantees that. And so basically now I need to know this thing, and this thing can be analyzed. And this factor, as you can imagine, this is basically the inverse Cardi, and this limit can be analyzed by analyzing some trick from our previous papers. So in the first route, what we did, we basically analyzed the integral on the real line, then use the Vitali porter to go the complex plane. We computed the limit, and then we know the limit. But then the disadvantage of this procedure is that this Vitali porter theorem tells you what the limit is, but it never tells you how the limit is approached. But if you want to make any statement about spacing, then you also need to know how the limit is approached. So what we did at the end of the day, we scrapped up all these theorems, and we just took the integral on the complex plane, and we just analyzed the integral instead of going through this route. But the point I want to make, without doing this, we wouldn't have dared to do the other homework, basically. So once we do all this, we have a result. And then I just want to make some final remarks. We already talked about this. Extension to large chiral algebra is possible. We can also do symmetry resolution. I actually told Indonil to look at it. And you can also talk about Virasoro main field theory, which is about the 4-point function instead of the partition function. You can try to make the connection to chaos more concrete than what it was in this talk. And of course, the holy grail is to prove dense spectra at fixed spin large scaling dimension, which we do not really approach in this talk, but that would be something would be very nice. Is the fixed spin large delta, not taking large spin, yeah. Because in the chaos literature, the idea is if you have some symmetry, you always go to some irreps, and then within each symmetry sector, you impose chaos. So that's the standard trick. Yeah. So that's where you would expect also, but this regime is very hard. As of now, it's very hard to handle, but maybe in few years we will get there.
Question, but you can tell me later, which is, I think, fully absorbed. So tell me later, what have we learned about, say, black holes?
Oh, by doing this?
So let's say my question to you is, we didn't assume anything about sparseness, blah, blah, blah.
Yeah. Yes.
Suppose you would apply to a gravitation.
Yeah.
Context. What have we learned already, and what do you think we can learn more if we impose the sparseness itself?
Oh, I think for large, and my intuition is that for large central charge, you probably need to assume sparseness to make sure these results holds true.
Sort of the gravity limit refers to is where you get C to go to infinity.
Yeah.
Sort of first, right?
Yeah.
Then you do various.
Yeah.
If you want to do that, you have to redo some.
Yeah, you have to redo some of these stuffs, yes. But I would imagine, like with the sparseness condition, some of these results will probably, all of them will go through with some appropriate sparseness condition. And then you will learn about how the spacing in the black hole microstates go like. And if you go to the near extremal limit, probably it will, for example, I always complain about like how how the correct, like in which regime of validity the correction actually makes sense to the near extremal limit, is log T correction and so on. So you have some statements in the grand canonical ensemble. This probably gives you some statement in the canonical ensemble, in the J beta ensemble, which would be nice, I think. And maybe also in the microcanonical ensemble. I'm not entirely sure about the microcanonical, but yeah, probably. So yeah, but but you need to do it more carefully, and I don't think the sparseness would be needed, because naively speaking, like what is the intuition of the sparseness? So think about the Cardy formula. In the dual channel, the vacuum dominates, and then you have bunch of heavy states. So what you do, that you forget about all the delta greater than C over 12 states, or you estimate it by some manner. And then in the usual case, C is finite. So number of states below the threshold always has to be finite. So the vacuum gives you some corrections, the leading answer. And then each of the terms gives you some exponentially suppressed correction. And because they are finite of them, so you can sum them up, they are still exponentially suppressed. So you forget about them. But now if you take C going to infinity, the number of states below the threshold has a possibility of grow very, very large. And then you cannot run this argument that each of the term is exponentially suppressed, hence the sum. And that's where exactly the sparseness condition comes in.
Exactly. So that we have to impose.
That,
and
yeah.
reasonable thing.
Yeah.
But then with that,
Yeah, with that, I would think that things will go through. Yes. I think with that, things should go through.
Thanks, Sridip, again.
Yeah.